All right, recording is rolling. So I've got a civil engineering PowerPoint for you guys. This is what I actually majored in back in college for my undergrad degree. Now, I've forgotten a lot of stuff because this was many years ago, although there's a lot of applications in this class that I've been able to keep up on just because it teaches on. But over a spring break, I cobbled together what I could remember from my classes back in university. So if you guys are going into engineering, especially civil engineering, then well, here's what I remember, maybe like the highlights of those days. So here's most of the classes I took. I may have forgotten one or two important ones, but there were some general classes like writing communication, ethics class, and those type of classes you have to take. Here's some math classes I had to take, calculus up through Calc 3. I did list trigonometry here, even though I didn't take that in college myself, but you use trigonometry all the time in physics and engineering, so gotta know that. Statistics, differential equations. Now this class was so far up, oh boy, this was a butt-kicking class to me, but this would be probably particularly applicable, I think, if you were in like fluid engineering or like aerodynamics, aeronautical engineering, maybe something like that. Science classes, obviously physics 1 and 2, chemistry 1 and 2. Physics 2 is more focused on like electricity type stuff. Physics 1 is more like mechanics. Physics 2 is more like circuits and that sort of thing. And then all these engineering specific classes. So, and I'll go through some of these with you guys. So statics, dynamics, statics is in dynamics, those are very similar to this class of physics. It's kind of like physics extended. There were specific classes just on materials like concrete and steel. Okay, so thermo, there were a couple of water classes I took. One was hydrodynamics, one was hydraulics. Those were pretty tough. But what we just solved, that Bernoulli principle problem we just solved, that might be like a very basic like hydrodynamics type problem. There's like soil mechanics. If you don't want your buildings to end up like the Leaning Tower of Pisa, better know what's going on with the soil. Transportation classes, how do you build a road? How do you build like a storm ditch? AutoCAD, although they did not call the class AutoCAD because I think that's like a brand name, but basically that's what it was. Project management class. Okay, so those are the classes that would fit the bill of some like a civil engineering course. Okay, all right, let's look at some of these one by one. Statics. So statics is the idea, if you build a static structure, that you could look at any individual point and all the forces have to sum to zero. That might give you some insight as to what parts are in tension, what parts are in compression. You guys remember right before spring break, I had you guys build a toothpick bridge. I told you guys where you put the forces so that basically the bottom of the bridge would go into tension and the top would go into compression. That might give you some insight how you want to build that bridge. But here's the physics principles, going back to many months ago in this class. So two-dimensional shape, like this 2D cutaway, we say, well, in the X direction or the Y direction, all the forces have to sum to zero. And on the XY plane, the torque has to sum to zero. You might call that about the Z axis if you use the right hand rule. If you have a three-dimensional structure, then it's a little fancier looking, but so we got the sum of the forces in each direction has to be zero, and also the sum of the torque about each axis also has to go to zero. Okay, so then do like a cutaway. I might pick this point of this truss system and figure out what's the compression and tension on each part. And then furthermore, if you know what materials that you made this out of, you say, oh, it looks like the compression on this part is more than the maximum compression of the concrete we're building. We better go back and like redesign that part of the truss system, something like that. There you go. There's statics. Oh, you know what? I had a trivia question for you guys, but I guess I'm kind of giving it away. Like, what's the strongest arch structure that you can build? Let's say I gave you guys a multiple choice of, should you use like a semicircle, like a dome? Should you use like a parabola arch? Or what this is actually the answer. This is the strongest arch you can create, like per like some parameters of some shape you're trying to prop up. It's called a catenary arch. And the mathematics of creating a catenary arch are, well, it's really fancy looking equation. I think you can. But physically, it's very simple to create one because it's the same shape that you get by just like hanging a chain from 2 points. So you get a perfect catenary like this. Now, if you take this, make it rigid, so it's in compression instead of tension, like turn it upside down, that's how you get a catenary arch. The St. Louis arch is an example of a modified catenary arch. Right? So it's the strongest arch structure you can create. So fun piece of trivia there. You see I-beams all over the place in engineering and structures. So what's the deal with the I-beam? Why is this so good? So imagine you took this I-beam and made it like your bridge back up before spring break. So maybe you prop up on one end and the other end. You got some support. Then you put a huge vertical load in the middle, like a weight pushing straight down, so that it bends it, kind of like your toothpick bridges a couple weeks back. Well, where would most of the stress be in this beam structure? Well, it's going to be in the very top and bottom flanks, because the bottom would take most of the tension and the top would take most of the compression. And in the middle, well, okay, there'd be a little forces, but most of it, again, would be in the top and bottom flanks. Okay, so if you have a beam that's shaped like that, that's why these wide flanks at the very top and bottom, well, that's where you want most of that material. Now, another reason for an I-beam type structure is, say if you had an I-beam set and then you filled all around with concrete. The concrete is much cheaper than steel. It's much more economical to build with concrete than it is steel. Okay, so if most of the stresses are going to be in the top and bottom anyway, you just fill in the rest with the middle with concrete, and that's an economical structure too. Also, this I-beam, here's the I-beam again, it's cut away, has an associated moment of inertia, and you can calculate that. We did this, I think back in December, something similar to this, like parallel axis theorem, whole deal. And anything has some moment of inertia has increased strength. So an example of that could be like a corrugated cardboard. Like cardboard, the material itself is like really flimsy paper, right? Now, why not just use really flimsy paper? Well, that would create a really flimsy box. But if you corrugate it like this, now it can handle stresses all different direction. How about this too? If you look on the side of a washing machine or a dryer, you'll see like indentations, like purposely put there, like manufactured, where it indents a little bit, like a couple of millimeters, and then indents back the other way. Why not just have like a straight panel of metal? Well, that would not be a very strong structure. Put a little crease in it, gives it a moment of inertia, gives it a lot more strength. Right? Dynamics. Classmates and I, back in the day, we used to call this class dynamics physics on steroids. You kind of get the idea. Let's look at this bottom right picture here. You might solve a problem like this. Dynamics might be particularly helpful if you're going into a class like, just a major like, what's it called? Mechanical engineering, or designing some crazy industrial process. Here we've got some kind of modified Atwood. Looks like string connected to this cart. I bet this angle beta would change as this cart's like moving, as this weight is falling. Maybe the cart is accelerating, but the cart is like stuck in horizontal motion. So how can you describe the motion of the cart based on like how far the weight fell? That'd be a really good dynamics type of question. So basically a really hard version of this class physics. Yeah, fun stuff there. Get into materials type classes. So concrete, here's components of concrete. Now, there's two main kinds of concrete that are used nowadays. There's Portland cement concrete, that's that gray colored concrete. And then there's asphalt concrete used to make roads. Here's a Portland cement concrete. Oh, there it is right there, Portland, right? Actually, I probably should not have included this picture here, this bottom left picture. This is, what's that really famous building in Rome, Italy? The Pantheon. This is an underside of that, the largest freestanding concrete dome. The Romans actually had a different type of concrete they used back then. So this technically isn't Portland itself, but there you go. There's ingredients to make concrete. Water, of course, is an ingredient. There's a chemical reaction that happens when you put it in the water. It goes through a curing process. Next couple of days, when you guys come in tomorrow, I'm going to have you guys build a sieve. So a sieve you can use to separate out a soil sample and see what mix of sand grain sizes do you have. Because if you have what's called well-graded soil sample, where you have large, medium, and small grains of rock sizes, that will actually create the strongest concrete. Because let's say you had like uniform grade, it says poorly graded here, wood poorly graded, uniform grade. A lot of the volume would be filled by, a lot of those voids would be filled just by the Portland cement, which is the weakest part of the concrete. The strongest part is actually the rocks. Okay, so the closer you have this well-graded, the stronger the concrete. Let's take a look at this graph down here. Got the grain size increasing to the right and the proportion passing through the sieve increasing going up. of course, it's cumulative because by the time at some point you got to add up all the sand grains. Right? And so well graded. Okay, so we got like some small, some medium, some large, and then it accumulates and you've accounted for all the soil. Something like uniformly graded, which would be poorly graded. This uniformly graded is poorly graded. Right? That would be like we don't have any small, and then bam, no, we get a bunch, and then not very much large, for example, right? And then gap graded might be like, okay, we get some of this, and then none of this, and then a bunch of this again. That's how you could say interpret that graph. Okay. So what's a sieve good for? Well, you have all these sieve layers. The top layer might have a large openings to allow everything through except for the largest rocks, right? And then they successfully get smaller and smaller, smaller until only the smallest particles, like the little dust and clay particles, are able to get all the way to the bottom. And that's how you can separate out and see what is your mix of soil sample. So ideally, you want a well-graded. So you want some of this and some of this and some of this. You want pretty even proportion all the way down. That will create the strongest concrete. Here are different strengths of concrete and what they could be used for, and also the mixing ratio of these different ingredients, cement to sand to stone. Now, if you are taking engineering classes in the States, they do use American units. So PSI, that's like pounds per square inch. Of course, in this class, we almost exclusively use metric system. So there's an equivalent strength in pascals, right? Maybe like megapascal. Oh, there it is. Here you go. So 2,500 pounds per square inch is equivalent to about 17 megapascals, right? 17 million pascals. And if you like, you could also quantify that in atmospheres, 170 atmospheres. We are sitting in 1 atmosphere of pressure right now, right? Something like that. Really strong concrete might be like 4,500 pounds per square inch, or 31 million pascals, or like 300 atmospheres. There you go. There's different uses for these things. Now, see these molds in the bottom left? These molds, the convention is to have these molds 4 inches diameter and 8 inches tall, these cylinders. You take these cylinders and put them in this compressor and compress that until it breaks, and then you can determine the compressive strength. I have right here one of these broken cylinders that I snagged from, I was taking the concrete class. Let's switch over. There we go. Right, concrete class. So we made some molds of different types of concrete. Here's 4 inches diameter. Oh, I got a ruler right here. I can prove to you guys this is 4 inches diameter. Right, there we go. Because we are in the States, we're using inches. Okay. And well, it was 8 inches high before this thing got busted. Right, so switch back over. Okay. Oh, actually, wait. Let me switch back to this thing because I want you guys to see a close up here. Let me do this for the video too. Stop sharing. For a moment here. Right. Let's take a good close look at this concrete. I'm zooming in here for class. Right. Ooh, do you guys see like some rock sizes here, like large rocks, and the voids are filled by the Portland cement, that gray cement. Ooh, look at that, right? So, I wonder what the grading is. Is this well graded or uniform graded or what? Well, could have determined by taking the soil before we mix this, put it into a mold, and put that through a sieve and separate it out that way. And that's going to be tomorrow's project. Tomorrow and the next day, have you guys build a sieve. All right, back to civil engineering. Oh. All right, wait for this to switch over. All right, here we go. All right, stress strain. I see a stress strain diagram here. So stress on the vertical axis, strain on the horizontal axis. So first of all, what are those? And then how do you interpret this graph? So stress is force per unit area. Hey, that's the same thing as pressure, isn't it? But it's pressure applied to solids. So like force per cross-sectional area, like this diagram here. This diagram down here at the bottom, I'm showing this being in tension, although you could reverse the forces and put it into compression, be same idea. And then as a result of some stress, there's going to be some percent change in the length, and that's what strain is. Strain is percent change in length as a result of that stress. So here's stress, force per unit area, strain, change in length per original length. Now, any particular material, well, it's going to have some strain as a result of that stress that's going to be unique to that material. And that property is called Young's modulus. Let's take a look at this graph, stress versus strain. So you put on some stress, it's going to strain. How much? Well, it depends. Is it concrete? Is it steel? Is it copper? Is it, what material are we talking about? The slope of this line, rise over run, is called Young's modulus, which again is unique per material. Now, this particular graph, I can tell you, is probably a metal like steel because beyond the yield strength, you can keep stretching, or compressing for that matter, before it eventually ruptures. Concrete, I can tell you, will rupture right about here. And then has none of the steel after the fact. So concrete, compress, 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 and then snap, breaks at the yield point. So let's say you did have a metal, like let's say you had a steel paper clip. You clip together a couple of papers and then pull the clip off. The shape goes back to the original shape. Anywhere in this linear part that involves Young's modulus is called the elastic zone. So you put on a stress, it deforms a little bit, you take off the stress, it goes back to its original shape. Once you go past this yield point, you get into permanent deformation. That's like if you paper clip together like 100 papers and it permanently deforms that paper clip. You pull the clip off, it's permanently deformed. Okay? Eventually go into a rupture. Right? Thickness of steel, what's Young's modulus and what's the average yield stress? How do you interpret this? Well, we got different thicknesses of steel, but do you guys see how Young's modulus for that steel is pretty well constant all the way down? Because we're talking about a material property. We're talking about, go back a slide here, the rise over run, Young's modulus, stress per strain is pretty well constant regardless of the diameter rod that you're talking about. But average yield stress, well, that's different. So it looks like for thicker bars of steel, we got increased stress that it can handle, right? So those numbers are different. Right? But do you guys see how these are both in pascals? I mean, gigapascals, megapascals, so some multiple of pascals. Now, why would that be? Why could the slope of this be in pascals and also the maximum value also be in pascals? Because strain is actually a unitless value, right? That makes sense. Change of length per length, meters per meters, that would cancel out. Okay, so the slope of this is in pascals, but the maximum value is also in pascals. Or PSI if you stuck in American units. Coefficient of thermal expansion. So we solved a couple of these yesterday. Heat up a material, it expands. How much? Well, it depends on the material. So different materials will expand differently. Right? But look at the last two rows here, steel and concrete. No, it's actually a window of values. It's not like a hard number like it's shown on this table. It's actually a window of values because you have different types of steel, different types of concrete, but they're pretty well the same coefficient of thermal expansion, which allows for things like this here, steel reinforced concrete. Steel reinforced concrete is a composite material. But to connect to the last slide real fast, the fact that they have the same coefficient of thermal expansion means that as the temperature changes, they'll expand and contract together, which means that it won't break apart the material. Now, why do you want steel reinforced concrete? What is this good for? Well, concrete, really, really good at handling compression, but terrible at handling tension. You pull on concrete a little bit and it breaks apart really easy. Ancient Romans had concrete. They had lots of concrete structures, but they did not have concrete like second floors like we are on right now because, well, you guys are seeing right here, like your guys' toothpick bridges, the bottom goes into tension. And if it was just concrete, that would snap apart really fast and would just crumble apart. But you throw down some steel rebar, the steel handles the tension part, right? And then the concrete above can handle the compression. Now you get have a really good composite material. Okay. See him putting down this rebar, pouring the concrete over that. Okay. Just like that. Now, eventually these structures will crack apart. I mean, just given enough time. Say you're creating like a parking garage. That might be what this is. I don't know. That looks like a permanent structure, like the school that we're in right now feels pretty permanent. But, you know, you let 1,000 years roll by, eventually it's going to crumble apart. That's where we get into something like this technology here. It's kind of a new technology, self-healing concrete. So how does this work? Well, there are some extremophile bacteria that will actually create calcium carbonate as a waste product. So if you include the bacteria and some starch that they could consume as food in the concrete itself, when you do get these cracks that form, those bacteria will be exposed to the air. They'll wake up from a dormant state. They'll consume those starches that are also baked into the concrete and excrete the calcium carbonate. And you have a self-sealing process based on this organic process. That's pretty cool. Other details about concrete too. There's like porous concrete if you want to have the water flow down to the ground water level. It's like groundwater. So because if you look at a city from above, if it's like covered in concrete and asphalt, you can imagine that a lot of water that used to get down to the groundwater could no longer get down there. So that might disrupt the ecological system from the rain. All right. And finally, I have a couple slides on water treatment. Now, I've forgotten a lot about water treatment. There was like a whole class I took on this, but at least mention the little bits I do remember. it's easy to forget about this part of the infrastructure because water pipes are all buried underground. It's easy to just take them for granted. You know, turn on the tap, you get water. Water flows down the drain and goes somewhere. Where does it go? But we are getting water, I want to say largely from the St. Johns River here in Brevard County. And that water, of course, has to be treated before you turn on the faucet so that it's safe to drink. In the States, we use chlorine to sanitize the water. In Europe, it's really common to use ozone to sanitize the water, just different conventions, I guess. Okay? But there's different filtration processes you can use to make sure it's safe to drink before it gets to your home. Now, each locality has different types of water, maybe different pollutants, maybe different minerals mixed in the water. So you do need a filtration process that's unique to each locality. And this is one thing you can do as an engineer is design unique filtration processes. Okay, how about water that flows down the drain? Well, you want to treat it before you send it back out into the environment, right? You don't want to just dump a bunch of raw sewage out into the environment. That's not good for anybody. So you have to treat this. And just like the clean water, this wastewater, there's different ways that you can treat it. So one method you can use is use bacteria to eat all the waste products so that when you do eventually dump the water back into the environment, it's a lot cleaner. You can also burn the wastewater, or burn the waste in the water, like allow the water to evaporate and then burn what's left behind. You can allow it to ferment, capture the methane from it and burn that for energy, right? Like a waste to energy type process. And so yeah, there's lots of processes you can use, but you want to treat your water before you dump it back out into the environment. And finally, roads. So if you are designing a road system, what does this look like? There's this whole structure underneath the road. You just see the top pavement, right? But there's this whole structure underneath it. So you want to put like large materials, large rocks and boulders down far below, and then successively smaller type materials until you get to the top. And most roads are made out of, or I want to say most are asphalt pavement, asphalt concrete, although you could use Portland cement concrete too, but asphalt is quieter, feels a little bit nicer to drive on, right? All right, so there you go. There's a quick rundown on civil engineering. We'll call that a wrap on today.